Okay, let's dive in. Today we're going under the hood, really peeling back the layers on something vital for Ruby. That thing working away behind the scenes, keeping your code running, the garbage collector. Or sometimes making it pause when you least expect it. Yeah, we've been digging into some great material from a technical talk given recently at RubyKaigi. It was all about this new experimental feature in Ruby 3.4 modular garbage collectors. So our mission here is to really unpack this. It sounds complex, but we want to understand why this is happening now after, 30 years of the same approach. And also how this modularity thing could actually be a big deal for performance, maybe unlock new speeds for different kinds of Ruby apps, like web servers versus background jobs.
That's right. And maybe we should start with the basics. Fundamentally, the garbage collector, the GC, it's Ruby's automatic memory manager. It's doing three main things. First, object allocation. When your code says new, the GC needs to find some memory for that object. Then, the really clever part, it has to figure out what's still needed, what's alive, and what's dead or garbage. It does this by tracing. It starts from known root objects, think global variables, constants, things currently running, and follows all the references. Anything it can reach is alive. Everything else, that's garbage. And the final step is reclaiming the resources used by that garbage, mostly memory, obviously. But it might also need to run finalizers, sort of clean up code or even close files. And yeah, it often manages this available memory using things like a free list to keep track of open spots.
Right, so it's this constant background janitor tidying up memory, and Ruby's had one for a very, very long time, hasn't it?
Oh yeah, decades. The default GC in Ruby uses an algorithm called mark sweep compact. It's pretty well understood. 3 phases, basically. First, mark. It goes through and identifies all those live objects we talked about, like putting a little check mark on them. Then sweep. It scans through memory, looks for anything without a check mark, and says, okay, this space is free again. It adds it back to the pool, maybe to that free list, and then there's an optional third phase, compact. Sometimes after sweeping, memory gets fragmented, lots of little gaps. Compaction shuffles the live objects together, squishes them down to one end of the memory region. This creates bigger blocks of free space, which makes finding space for new, especially larger objects much faster later on, often uses something called the two-finger algorithm to do this moving efficiently.
Okay, so it sounds solid. Mark, sweep, maybe compact. It works. It's been improved over 30 years.
Yeah.
So why do I talk about totally different GCs now? If it ain't broke.
Well, it's not broken exactly, but it definitely has limitations. Limitations that are becoming more noticeable as Ruby gets used for more demanding, diverse things. While Mark Sweep Compact is, simple and generally effective, its design choices create some inherent bottlenecks. These can impact performance, especially things like latency in web apps or just raw throughput in data processing.
So what are the alternatives, and why haven't they just been dropped into Ruby before?
Good question. There are other well-known algorithms. Take reference counting, for instance. Python uses it a lot. The idea is simple. Keep a count for each object of how many things point to it. When the count hits 0, poof, the object can be freed immediately.
Sounds efficient. Quick cleanup.
It can be for latency, but it's really hard to get right in Ruby. It needs something called write barriers. Basically, the GC needs to be notified every single time a reference is created or destroyed so it can update the counts. Ruby's internals just weren't designed for that level of notification. There are places where references change without telling the GC, which would totally break reference counting. You'd get memory leaks or crashes.
Okay, so that one's tricky because of Ruby's design. What else?
Another big one is semi-space copying. This one's conceptually neat. You split the memory heap into 2 halves, a from space and a to space. You allocate new objects really fast in the from space, just bumping a pointer along. When it's full, the GC kicks in. It finds all the live objects in the from space and copies them over to the to space. As it copies, it automatically packs them together tightly. Perfect compaction, basically. Then the role swap. The old from space is now empty, and the to space becomes the new from space for allocations.
That sounds great. Automatic defragmentation built in. What's the catch?
2 main catches. First, it uses twice the memory, because 1/2 is always idle. That can be a big deal. But the killer for Ruby is that all live objects must be movable. The whole point is copying them. Ruby, however, needs to support pinning. Certain objects, especially those interacting with C extensions or system libraries, absolutely cannot change their memory address. Semi-space copying just fundamentally can't handle that, so it's out as a direct replacement.
Okay, so pinning is a major constraint. Can't move everything.
Exactly, but there are hybrids, like an algorithm called IMEX. It tries to get the best of both worlds. It combines ideas from mark sweep and copying. It might divide the heap into smaller blocks, identify which blocks are badly fragmented, and then during the marking phase, it can choose to move objects, but only within those specific fragmented blocks. Crucially, it's designed to respect pinning. If an object is pinned, or if it's in a block not being compacted, it just stays put.
Ah, so it gets some compaction benefits without needing to move everything.
Right. It's a compromise, but one that could actually work within Ruby's constraints. It makes IMIX a much more plausible option.
Interesting. Okay, pinning is one big constraint.
Yeah.
You also mentioned bottlenecks.
Mm.
What about hardware? We all have multi-core CPUs now. Does the current GC take advantage of that?
That's another huge area, yeah. And the short answer is mostly no. The standard Ruby GC cycle is predominantly single-threaded. Even if you're using Ruby threads, the global interpreter lock means you're not getting true CPU parallelism for your Ruby code anyway. But the GC pause itself stops all those threads. Everyone waits.
And what about reactors? They can run in parallel, right?
They can, but they all share the same memory heap and therefore the same single-threaded GC. So when the GC needs to run, all parallel reactors have to start and wait for that one GC thread to finish its mark sweep compact cycle. It becomes a major scalability bottleneck.
Wow. Okay, so parallelism is a big driver for looking at alternatives.
Definitely. And there's one more piece. Memory allocation flexibility. Historically, Ruby objects were simple. For a long time, the internal C structure for every Ruby object was a fixed 40 bytes. If an object needed more data, like a large string, that data had to be allocated separately using the standard system malloc.
40 bytes, that seems tiny.
It was simple for the GC, but not always efficient. Lots of small malloc calls, potential for poor memory locality. Ruby 3.2 improved this quite a bit with variable width allocation, or VWA. Peter Zhu was a co-author on that work. It allows for a few fixed larger slot sizes, 40, 80, 160, 320, 640 bytes. Better, but still fixed steps. Anything bigger still hits malloc.
So still not fully dynamic based on actual need.
Right. Ideally, you'd want the allocator to handle a wider range of sizes more smoothly, potentially reducing waste and improving how data is laid out in memory. And different GC algorithms often come with different, more sophisticated allocation strategies.
Okay, so let's recap the motivations. We've got different algorithms offering different trade-offs, maybe better latency, maybe better throughput, maybe less memory overhead. We have the lack of parallelism in the current GC being a bottleneck, especially with reactors. And we have limitations in how flexibly memory gets allocated. It seems like a strong case for change. So back to the earlier question.
Yeah.
Why not just pick something like IMIX, which seems compatible, and make it the new default?
Yeah, it's a fair question. But the core team made a very conscious decision not to just rip out the old GC and replace it wholesale. Firstly, as we said, GCs are all about trade-offs. Mark Sweep Compact, despite its limits, is incredibly battle-tested. It's memory efficient, reasonably fast for a huge range of common Ruby tasks, from tiny scripts to massive web applications. There's just no single best GC for absolutely everyone. What's optimal for a low-latency web server might be terrible for a memory-hungry batch job.
One size doesn't fit all.
Exactly. And secondly, think about the future. Let's say they pick the best algorithm known today, did a massive rewrite. What happens in 5 or 10 years when someone invents an even better GC algorithm?
We have to do it all over again.
Right, you'd be stuck in the same situation.
Yeah.
So the thinking shifted towards making the GC system itself flexible. Instead of choosing one new GC, enable Ruby to use different GCs.
Ah, and that's where modular garbage collectors come in, this experimental thing in 3.4. How does that work?
The fundamental idea is to decouple the specific GC implementation, the mark sweep logic or AMIX logic or whatever, from the Ruby virtual machine's core. The first step was code surgery. The old gc.c file, which did everything, was split up. The new gc.c is much smaller. It handles the high-level interface with the rest of the VM starting GC, stopping it, interacting with reactors, managing flags. The actual mark sweep compact implementation code, that got moved into its own file, gcdefault.c.
Okay, so the default logic is now separate. How does that help swap things?
Because now that gcdefault.c or any other GC implementation can be compiled as a separate shared library, like a .so file on Linux or a .dlib on macOS.
Like a native extension.
Exactly like a native extension. It can be loaded dynamically by the Ruby VM at runtime. You could potentially tell Ruby, okay, don't load default.c, load this other GC library instead.
Wow. Okay, but how did the VM and this loaded GC library talk to each other? There must be some kind of contract.
Absolutely, that's the crucial part. The Modular GC API. It's a formal interface defining how the VM and the GC module communicate. It really has two sides. First, there's the API that any modular GC must provide. This is defined in a header file called gcgc.pull.h. It lists about 60 functions, grouped into roughly 14 categories that the GC needs to implement so the VM can control it.
Like what sort of functions?
Things for booting up and shutting down the GC, allocating its internal data structures, functions for the VM to tell the GC, okay, run a collection cycle now, or enable yourself, disable yourself, here's some configuration. Critically, it includes the function for allocating memory for a new Ruby object the VM asks, and the GC returns a pointer to the memory it found. Also functions for the VM's marking process to tell the GC, hey, this object is alive, functions to handle those pinning requests we talked about, and functions to receive write barrier notifications if the GC needs them.
So that's what the GC exposes to the VM. What about the other way around? Does the GC need things from the VM?
Yes, that's the second part of the API, defined in gcgc. These are functions the GC implementation is allowed to call back into the VM. They aren't part of the normal public C API for extensions because only a GC would need them. Examples include ways to lock the entire VM state for safety during GC, ways to stop and resume reactors, and really importantly, a way for the GC to ask the VM, please walk the references for this object. The GC doesn't need to know the messy details of how Ruby objects are structured internally.
Ah, the abstraction.
Exactly. The GC just says, VM, tell me who this object points to, and the VM handles it. This means Ruby's internal object layouts can change in the future without breaking every single GC implementation. The API also includes functions for the GC to tell the VM, okay, I've determined this object is dead, you can run its finalizer now, or do other cleanup.
That separation sounds incredibly well thought out. It keeps the GC focused on GC logic and the VM focused on Ruby logic. And you said this is actually buildable now in 3.4.
Yep. It's experimental. You need to enable specific build flags, but you can compile Ruby 3.4 with this modular GC support. There's a guide in the Ruby source repository, I believe. When you build it this way, the default Mark Suite Compact GC we've been talking about is actually compiled as one of these separate loadable libraries.
So the default itself uses the new API.
Correct. But the really exciting part is that Ruby 3.4 also ships with experimental support for the first major alternative GC using this new API, MMTK.
MMTK. Okay, what's that?
MMTK stands for Memory Management Toolkit. It's a big project developed primarily at the Australian National University. It's written in Rust, and importantly, it's designed to be language agnostic. It's not just a Ruby thing.
So a general-purpose GC toolkit.
Pretty much. It's really a framework that contains a whole collection of different GC algorithms, which they call plans. And because it's language agnostic, it's already been integrated with several other major language runtimes. It's used with the JVM for Java, with Julia, and even with Google's V8 JavaScript engine.
Wow. So it's quite mature and used elsewhere. What kind of plans does it offer that might be interesting for Ruby?
It has the basics like simple Mark Sweep and Mark Compact plans, useful for comparison. It has a no GC plan, just for testing the integration itself. It does have a semi-space copying plan, but again, that one likely won't work well for Ruby because of the pinning requirement we discussed.
Right.
But crucially, it does have implementations of IMIX, that hybrid approach which can support pinning. That's a key one. They also have more advanced experimental plans, like one called LXR, which apparently combines reference counting ideas with IMIX. It's shown some promising results for reducing pause times, latency in OpenJDK environments.
Interesting. And what about parallelism? That was a big limitation of the default GC.
That's a major strength of MMTK. It was designed from the ground up with parallelism in mind. It uses a concept called work packets. It breaks down the GC work like marking a section of the object graph or sweeping a memory region into small independent units. Then multiple worker threads can just grab these packets and process them concurrently. It's built for multi-core systems.
Okay, so MMTK brings a whole suite of modern parallel-ready GC algorithms. How is it actually connected to Ruby through this new modular API? Is it complex?
Well, there's a bit of history. The MMTK team actually started experimenting with Ruby back in 2020, but that involved maintaining a separate fork of the Ruby interpreter. They explored some really novel ideas there, like using sidecar objects to store GC metadata alongside Ruby objects.
Okay, so an earlier research version existed.
Right. The current effort, the one integrated with the experimental Ruby 3.4 feature, is much newer, less than a year old, really. Its focus is specifically on using the official Modular GC API so it can work with mainline Ruby. No fork needed.
And the architecture. How does Ruby talk to this Rust toolkit?
It's layered. At the top, there's a C binding layer. The C code implements those 60 functions required by the Modular GC API, gcpool.h. The C layer then calls into a set of Rust bindings. These bindings act as the bridge between the C world of the Ruby VM and the Rust world of MMTK. Finally, these Rust bindings talk to the core MMTK library, which is included just like any other Rust dependency using cargo. The Rust bindings also contain Ruby-specific logic, like defining exactly what an MMTK work packet means in terms of Ruby objects, how to mark one, how to scan its references via the VM callback, how to free it.
Got it. C interface Rust bridge, core MMTK Rust library. And how's it performing? Is it faster yet?
So it's important to set expectations here. This is still very much a work in progress. Right now, this modular GC version of MMTK for Ruby is actually slower than both the original MMTK research fork and even Ruby's default Mark Suite Compact GC.
Oh, okay. Still early days.
Very early days for this specific integration. The plumbing is there, the communication works, but the performance tuning hasn't really happened yet. The source code is available, though, in the RubyMTK GitHub repository if you want to look.
Makes sense. So, given it's experimental and currently slower, what's the roadmap? What are the next steps to make this MMTK integration actually deliver on its promise?
The main goals are pretty clear. First is performance parity, then hopefully superiority. A big part of that will be enabling MMTK's more advanced moving plans that do support pinning, like a sophisticated version of IMIX that can compact memory more effectively. That should give a significant boost over the current simple, non-moving plans being used.
Okay, better compassion. What else?
Another major target is enabling generational GC. This is a classic optimization technique used in many high-performance GCs, like in the JVM.
How does that work, roughly?
The basic idea is that most objects die young. You create an object, use it briefly, and then it becomes garbage very quickly. So a generational GC divides the heap into usually a small young generation and a larger old generation. New objects go into the young generation. The GC then collects the young generation much more frequently, because that's where most of the garbage is likely to be found. It only needs to do a full, expensive scan of the old generation much less often.
Ah, focus the effort where it's most likely to pay off.
Exactly. It drastically reduces average pause times. MMTK has plans designed for this, like one called Sticky IMIX, so integrating that is a key goal.
And parallelism, making it faster on multi-core.
Yes, improving parallelism further. While MMTK is parallel internally, making it fly with Ruby requires more work. This involves defining more fine-grained work packets that are suitable for Ruby's object graph structure. And also, carefully making sure all the different phases of the GC cycle when interacting with the Ruby VM state are properly thread-safe. Remember, the default Ruby GC wasn't designed with the assumption that multiple threads might be doing GC work simultaneously on its internal data, so there's careful synchronization work needed there.
Wow, okay, that really has been a deep dive, hasn't it? From the basic job of the GC, understanding Ruby's long-standing Mark Suite Compact, through its limitations around things like pinning, parallelism, allocation, seeing why just replacing it wasn't the right move, and landing on this really elegant idea of modularity, making the GC pluggable. And then seeing the potential with something powerful like MMTK coming into the ecosystem, it really makes you reconsider performance tuning. You know, maybe some of those weird, hard-to-debug slowdowns you hit weren't your code, but the GC pausing awkwardly or fighting against fragmentation. Things that this modular approach could eventually let you control.
Precisely. It opens up choices. And while, yes, we have to stress, the modular GC API and the MMTK integration are definitely experimental today, you wouldn't ship a production app on them yet. The framework itself is there in Ruby 3.4. You can build it, you can play with it, you can start thinking about the possibilities, which kind of leaves us, and you the listener, with a really interesting thought, doesn't it? If you could choose, or maybe even help build, a garbage collector specifically tuned for the memory usage patterns and performance needs of your specific Ruby application, what would that look like? What kind of bottlenecks could you eliminate? What new levels of performance or efficiency might become possible for Ruby in areas where maybe people didn't think it could compete before? It's quite exciting to consider.
That is a fantastic question to leave things on.
Mhm.
What GC would you choose? Definitely food for thought. Thank you for joining us on this exploration into Ruby's garbage collection future.